So I'd like to go ahead and invite our next speaker up to the stage here, Josh, who is going to be presenting a talk entitled FASER, Binary Code Similarity Search Through the Use of Intermediate Representation. So without further ado, Josh.
Be worth the wait. Okay. Hello, everyone. So yeah, so as I was introduced, my name's Josh. I'm doing this presentation on behalf of Loughborough Uni and the Alan Turing Institute. I'm a PhD student, part-time, and my day job is a machine learning engineer embedded in a vulnerability research team at a company called Roke in the UK. I'm really jet lagged. So if I kind of pause randomly, it's because my brain hasn't quite caught up with me. So the kind of plan for the talk, I'm going to start with a bit of a background. I'm going to go through our contribution and the kind of approach that we've come up with. I've got a number of experiments and then some results to show you guys, and then hopefully conclude with some questions, as long as I don't overrun. So background-wise, so what is code similarity search for the folks in here that aren't aware of it? It's essentially an information retrieval task. So the kind of problems you're setting up is given a query function or some sort of query. Is that query within a big corpus of related things? So in this case, other binary functions. It's been used for loads and loads of different kind of use cases and different tasks within particularly academia. So there's things like identifying end days. So a lot of this research has been focused on firmware and IoT. So yeah, can we find the newest vulnerability in loads and loads of different software at scale? There's quite a lot of research about open source libraries, and can you detect open source libraries in firmware, which is another interesting problem. There isn't a huge amount of research, but there's a growing kind of area around can we look for function reuse in malware? I guess the challenge there is finding the function you search for, given some of the techniques they use, but that's kind of a growing area. And the research I've primarily been looking at myself is how to actually support reverse engineers transfer their knowledge from one target to another, which is, yeah, a very interesting problem. So for those who are aware of binary functions, it's been around for a while. So I guess it's not new. So it's been typically solved with natural language processing or graphs. So a lot of that's been done at an assembly level or bytes in the NLP case. And graphs, they primarily use an approach called attributed control flow graphs, where they essentially process functions or basic blocks to then give you a vector for each node. It kind of the most kind of I guess the OG approaches, I guess, were ASM2VEC, SAFE, and Gemini. So both of those, so ASM2VEC and SAFE are NLP approaches, and Gemini is a graph neural network approach, and that was in the kind of the tens. Newer approaches, particularly around NLP, have tried to use some of the kind of advancements in transformers. And as I said, I've mentioned three there. So JTrans, Palm Tree, and Trex. All of them use either BERT or Roberta, and then they use the standard kind of pre-train, fine-tune kind of methodology. The thing that is quite interesting with these is they've all come up with their own kind of pre-training kind of methods. So, for example, next sentence prediction doesn't work in an assembly case. Oh, wonderful. Yeah, so I did next sentence prediction, for example, doesn't work in an assembly case because if you some assembly instructions might actually be a branch instruction or something. So actually predicting the next instruction doesn't quite make sense in this case. And a lot of the research is sometimes cross-architecture, but most of the time it's cross-compilers. So can we find the function from GCC 4 to GCC 10 or whatever? And frankly, a lot of the researchers do that by stealth, which is very annoying having to read them because you're trying to work out what are you actually doing. So our contribution. So I'm going to go through the last point in detail. The paper covers the other three, but I'll kind of go through it quickly. So the biggest thing we're using is, rather than BERT or Roberta, we're using Longformer, which is a long context transformer. It changes the attention mechanism so you get over the quadratic scaling complexity, and uses kind of a windowing feature, which is really useful in this case. We also ditch the pre-training approach. So a lot of transformers, and unless you're using a transformer for loads of downstream tasks, I personally think the pre-training approach is a bit of a waste of time if you're only going to use it for one thing. So we get rid of that and we just focus specifically on the binary function search task. We also use Radar 2's intermediate representational ISL instead of bytes or assembly for an NLP use case. And the primary reason for this is that it's innately cross-architecture already. It's been designed to be cross-architecture. Just to link back to the long former, if you do go to an IR, typically the instructions are much longer. So that's why we've had to go for the long form architecture to actually get the amount of instructions, a similar amount of instructions in. And then, as it said, that last point about deep metric learning and a number of things which I'll go through. But we basically use deep metric learning, which some of the approaches have used, but not explicitly said they're using. And yeah, it's leveraging the research coming out of facial recognition and stuff like that. So as I said, I'm going to focus on the last one. So yeah, double-edged sword. So has anyone trained metric learning, deep metric learning? Did you have a good time? It's really good if it works and really hard otherwise. So as the diagram shows, you're basically trying to move your kind of feature space to basically cluster stuff together. So you want similar things to be close to each other in an embedding space and dissimilar being further away. So it's typically driven by some sort of metric, which is usually distance. In our case, it was coincide similarity. As I say, it's very frustrating to train. It collapses loads. And it might do it after like 15 hours of training or like 5 minutes. It's quite frustrating. And it also typically requires very large batch sizes. So if you look at some of the facial recognition stuff that uses this, they're using like thousands of images. And then they're training it on CPU, which again, sounds like a bad time. But we persevered. So one of the big things we added, which a lot of the prior research in particularly binary function search doesn't use, is actually to mine the pairs dynamically. So most of the research uses pre-computed pairs. So they'll essentially do like Python iter-tool combinations and then kind of save that. So the general process when you dynamically mine is you basically create a batch, you embed everything, you dynamically make positive and negatives within that batch, you generate the losses for them, and then you use some sort of aggregation or some sort of rule after something like if it's above 0 or what's the mean or something like that. And the thing that this kind of provides you is that you're constantly challenging your model's weaknesses. So the particular rule we use, which was basically pick the hardest ones all the time. So in the case of cross-architecture search, your model might quite quickly learn to do ARM versus MIPS, but might not be very good doing ARM versus x86. And this approach will consistently kind of challenge that. We also, some of the losses that are used in deep metric learning, like cosine embedding loss or margin loss and stuff, we realized were the source of our pain and were the thing that were making it collapse. So when we're dynamically mining and we're picking the hardest pairs, we were, particularly at the beginning of training, the loss was so all over the place that the model just kind of degenerated and just kind of broke. So we adopted circle loss. I'm going to admit it works. I'm not 100% sure why it works. And the paper that's written is very dense. So yes, I'm probably gonna butcher this. But as I said, it's used quite a lot in facial recognition, particularly fine-grained facial recognition when you have you've filtered a large number of individuals, and then you've actually got like a very small subset of very similar individuals, and you want to actually try and pick out the person that it is. So one of the big things which is different is it has a circular decision boundary, which the paper purports to allow you to then actually get a more fine-grained kind of embedding, because you're actually allowed to, rather than doing things in lines, you can start pulling everything together. The thing that's quite interesting, and the last 2 points, it emphasizes suboptimal similarity scores, reweights them in a way that when you have a large variation, it kind of smooths it out for you. Particularly when we were looking at loss curves and stuff like that with this, the loss was much smoother than kind of the crazy start using something like margin loss or cosine embedding loss. So we've got to put an obligatory architecture diagram in, obviously. So yeah, so you'll kind of see that we start with a tokenizing encoded ISL strings. It goes into a long form, 8 long former blocks, and then slowly gets compressed down to a 128 embedding. Experimented with the kind of size of the embeddings, and particularly for performance. In our case, having a smaller embedding allowed us to search over much larger pools of functions. And the B diagram is slightly wrong, so I'm just going to skip over that. So the data set wise, so we reused the work from Maselli et al. 2022. That's Cisco Talos have released quite a large data set of binaries compiled ARM, MIPS, x86, various different bitnesses all over the place. So it's quite a large data set. And as you can see, they're the projects which I won't worry about. Once we've processed them, you end up with about 1.5 million functions. And that's after a number of kind of cleaning steps. There's some normalization that happens. There's also a thing that a lot of papers aren't doing, which is deduplicating them. So let's say we have a function, let's say memcopy, we'll only have unique versions of memcopy. There won't be multiple versions of the same function in there. Because we found that regardless of compiler or optimization or even architecture, sometimes you might get the same function in ISL, and then it helped us to kind of fill them out. We also had another data set which comes as part of the paper, which is vulnerability based, which is 14 open SSL CVs across ARM and MIPS. And again, we picked that up. So experiment-wise, so the first experiment was just a general function search, and the objectives there. So, given a query function, can we search across what's known as a search pool where there's 1 positive function and 100 negative functions? And the task within the Maselli et al. Paper is called XM, and this has no constraints on bitness, architecture, compiler at all. So it's basically real world, like you're not necessarily sure what you're going to go up against. And the metrics wise are reported in the paper, and we've adopted them too. Recall at 1 and MMR at 10, mean reciprocal rank at 10. It's worth noting for those who are new to information retrieval, recall, precision are not the same as doing classification. They're subtly different. And in the paper, I think there's been a slight confusion from the authors that they're actually doing precision at 1, and recall at 1 only works because there's only 1 positive in their results retrieved. But anyway, we ran with it. So we made 2 versions of the model, one that was register normalized and one that wasn't. The normalization for the registers was for a 32-bit register, it was just reg 32. The token was reg 32, and for 64-bit, it was reg 64. For some reason, and we're currently we're trying to do some experimentation on working out why this is. The non-register normalization model actually performs better at general function search. And we think this is because, particularly with MIPS, when you compare 2 functions that are similar, the order I'm going to explain this, the registers they use are the same, but the order is completely different. So yeah, we think it might be kind of doing something, kind of mapping the different register use. And we compare against 3 other approaches. The ones with the ref 13 were the best ones within Maselli et al.'s paper. The thing to note with the GMN one for the next experiment, that is it's called graph matching networks, and it requires you to compare every single possible combination of a search pool, which at scale, doing millions and millions of kind of searches every time you searched, it would just be completely unscalable. So the next one. So we then did the vulnerability search one. So again, I'll try and explain this. If it doesn't make sense, someone please tell me. So the authors have identified 2 pieces of firmware, one for a Netgear router and one for a TP-Link mesh thing. And within that firmware, there is vulnerable libcrypto libraries within it. So they've taken those 2 out. One's ARM and one's MIPS. And then they've compiled the same library and the same version of the library for a number of different architectures. And then the goal is you use the compiled version, you take the vulnerable function out of it, and then you search the firmware image. That's the kind of, does that make sense? Yeah, maybe? Okay, we'll see. So results-wise, what you're seeing here, so let's just start from the top. So I'm only showing you the ARM32 results, which is a Netgear router. So the columns ARM MIPS x86, x86-64 are the version of the compiled firmware that we've taken the vulnerability from. And what you're seeing there are the ranks of the vulnerability when it was returned on the search. So 1 means of the 1,000 functions within the firmware image, it was position 1 when the model searched. And as you can see, to our surprise, may I add, that the register normalized one performs really, really well. We've done some additional experimentation across a broader set of vulnerabilities. I know some of one of the reviewers picked it up. That is quite a small data set, which is completely fair. We've done a search over a number of Android vulnerabilities, and it kind of holds up. Within, if you did kind of the top 10, you're likely to get the vulnerability within. But it definitely isn't, quite as good as this says, which is a shame. We also did as well an experiment which I've been in particularly government research for quite some time in the UK, and I get quite frustrated when a paper is all good news stories. So I thought, you know what, I'm going to put a bad news story in mine. So I tried a zero-shot experiment using RISC-V as the libcrypto version, and then conducted the same search again. As you can see, the model's rubbish, which is cool. But the thing that is interesting, and it was a hypothesis we kind of wanted to prove out and hoping to prove out, is there's been a couple of papers published that say ARM32 is statistically closer to x86. And this kind of is a natural occurrence across a number of different embedding models. And we had a hypothesis of, I think RISC-V will be closer to MIPS because it's a derivative of MIPS. And this seems to kind of hold out slightly, loosely. But yeah, this was just some results we're going to show. So to conclude, had to include a meme. So forgoing the pre-training seems to work. And I think for a lot of folk, if you are training professionally, I've adopted this approach to it, and it is better if you're not using them for downstream. If you're not using them for multiple downstream tasks, this definitely works. Using an intermediate representation seems to work. The primary benefit of it was that other than having to normalize it, you just chuck it in. So rather than having to do, there's a lot of kind of post-processing, particularly architecture specific, that people are doing. But with this, you just have to normalize once and off it goes. MIPS, as the meme says, is still an issue. Not good enough for zero-shot architecture search, which isn't surprising. And I guess one of the areas we're going to explore and maybe come back here talking about is we want to have an understanding of what the functions is the model struggling with. There's also a growing area of how can we pre-filter functions. So people are using like symbolic execution and taint analysis or whatever to basically reduce the search pool. So if you have millions of functions, and you just cut out 95% of them before you even start doing this stuff. And there's also an interesting area of using decompiled code. So could you use a decompiled code to inform approaches like this? Also, I forgot to put this on my slides. All of the codes, the data processing tool, the models and the data are all on GitHub. So it's linked in the paper. So if you want to copy any of it, whatever, be my guest. Unless you adversary MI folk, if we release a paper saying it's rubbish. So hey, we'll see. But yeah, any questions?
So I think we have a few minutes for questions here.
So I noticed you were using Siamese networks to train this from scratch. Have you looked at like online contrastive losses?
No.
Okay, because I imagine you're going to have to retrain this thing every time there's a new vulnerability found.
So yes, I think it's something we've definitely we have from conducting some of the other kind of experiments which aren't necessarily in the paper. There does seem to be particular kind of classes of vulnerability that it's constantly messing up on.
Mm-hmm.
But I guess the hypothesis and hopefully the aim of it is to have a general model that can create embeddings that you can compare against. So even if you've got a new vulnerability, you should be able to put in the vulnerability as it was compiled and then still be able to find it. But yeah, it's yeah, game we play. Yeah. Thank you.
So I see we have a couple of questions on the chat. Is it easier or possible to get intermediate representation starting from a binary, or do you have to start from the source code and run it through compiler tools?
So just to be clear, this is all from binaries, so compiled binaries. So yeah, it has to be compiled for this to work.
Thank you. Another question on the chat is, have you thought about using the intermediate representation and applying it to malicious or benign file classification?
I have not.
Other questions?
Actually, I'm not sure if you mentioned it here, but in your paper, you mentioned truncating functions that are beyond a certain size. Have you considered going down to a different granularity, like looking at basic blocks or removing other things like maybe the function prologues from, functions?
So yeah, so in the paper, we due to the size of the long form as input, we truncate some functions to anything longer than 4,096. We have to truncate. We've had an idea of whether or not you could do you start at the bottom of the function, and so you remove all of the prologue and whatever, and you kind of do it from the bottom up. There is a couple of research papers that do it at a basic block level, and that is again something we're trying to explore of can we embed basic blocks and then use like a GNN as some of the other folks have mentioned. All right, Steve.
Thanks, that sort of led into my question. I'm just wondering, so I'm thinking of a function as a graph of basic blocks. I'm wondering could you talk a bit about the representation exactly that's going into your model?
Yeah, so it's basically linear disassembly. So starts from the top, we ignore branching, anything, we just basically take in, concatenate all of the IR representations for every instruction into one big string and then chop it at a particular length. So yeah, thank you.
Yeah, I think we have time for one more question.
Well, there's a dude at the back.
Okay.
Oh. Just talk loudly.
So you picked the radar intermediate representation. There's a bunch out there and it's like almost a religious war. Which one's the best? So why did you pick this one?
Oh no. I knew this would come up. So the primary reason, so I'm not in any camp, so I'm happy to use any. The primary reason was the tool's open source. You can easily script it. But that was the primary kind of reason for it. I think also some of the IRs like P code and Vex are really verbose. So it takes a lot of normalization and filtering and stuff to do it. And the big kind of benefit of Radar 2's one is it's just a string. So you can just regex the stuff out and stuff. So that's basically the motivation for it. We think, I wouldn't be surprised if someone did the effort of doing the normalization for other IRs. I wouldn't be surprised if it worked as well, if not better than what we've come up with.
Great. Let's go ahead and give Josh another round of applause.